6.1 exponential growth and decay functions. What are some of the characteristics of the graphs, and what are the general forms, including compound interest? So the graphs, you have an equation, f of x equals b to the x, and if b is greater than 1, it's going to be an exponential growth. If b is between 0 and 1, it's going to be an exponential decay. Makes sense because if you have, for example, b as 1/2, 1/2 to a certain power is going to get smaller and smaller and smaller as the power increases. So what are the domain ranges? You can see on both of them, they're the same thing. Domain, all real numbers. Range, all numbers greater than 0 to infinity. There's also a notion of asymptote, and an asymptote is a line that the graph approaches more and more closely as x goes to infinity or negative infinity. And you're going to see in both of these cases, the asymptote is going to be the x-axis, or y equals 0. Taking a look at a couple of equations and graphing them, this is going to be an exponential growth, and this is going to be an exponential decay. Growth because this is greater than 1, decay because it's between 0 and 1. So a growth looks like this, and a decay looks like this. And now we just need to put some numbers in. So what are the numbers as you go ahead? If I put 0 in for x, for the 0 is 1, so you know that that's going to be 1 point. And if you put 1 in for x, you end up getting 4. So there's another point. Similarly here, you put 0 in for x, you get 1. You put 1 in for x, and you're going to get 2/3. Tell whether the model represents exponential growth or decay. All right, so you're focusing on this one, and we can rewrite this as y equals 25 times 1 minus 0.15 to the power of t. This is between 0 and 1, so we know it's going to be a decay. Identify the annual percent increase or decrease. This right here is talking about the rate. And so you know that it's going to decrease in value by a rate of 15%. Now, if this was more than 1, it'd be 1 plus a number, and that number would be the decimal form of a percent, and it would be an increase. Now, let's take a look at this problem, and you're focusing on the remaining amount of radioactive material, where A is the initial. Now, it doesn't say what is the initial. It says what percent of the this chromium 51 decays each day. So the problem is you have an exponent here of t divided by 28. So again, what you want to do is rewrite this as a different form to help you with the growth or the decay. So this is 1 over 28 all to the t power. All right, and so what you get here is when you plug that in, y equals a to the 0.98 to the power of t, which means y is equal to a 1 minus 0.02 to the power of t, which means that it's going to be a decay of 2% each day. So putting it in the form of exponential growth or decay, and then changing that number to 1 minus or 1 plus a number shows us the percent increase or decrease. Now, you could also have a compound interest type of problem. And compound interest means it could be monthly, quarterly, semi-annually. And there's an equation for this where it's the ending amount equals the beginning amount times 1 plus the rate in decimal form divided by the number of times it's compounded in a year to the power of number of times it's compounded times the number of years. So it says you deposit this that pays that. Find the balance after 3 years when the interest is compounded quarterly. Compounded quarterly, we go to this compounded situation. A equals the principal, 9,000, how much you deposited. 1 plus the rate, 0.0146, compounded quarterly, every 4 months. So, every 3 months means it's going to be 4 times in a year. And then it says 3 years, so it's going to be 4 times 3. All right, so now when you plug that in your calculator, let's see, 9,000 times parentheses 1 plus 0.0146 divided by 4, and then that's going to be the power of 4 times 3 or 12. And that answer ends up being $9,402.21.